All right, welcome to lecture number 14 in this series on algebraic topology. I'm Norman Wildberger. Today we're going to talk about the Ham-Sandwich theorem and a few other results that are related to it, carrying on from what we did last time. So let me remind you what we did last time. We ended up with the lemma of Borsuk, which involves the antipodal point of a point. So there's our circle. Antipodal point of P is P star. And the lemma was that if we have a continuous function from the circle to the circle with this particular property, that it sends the antipodal point of a point P to the antipodal of where it sends P. So whatever it does to P, it's got to send P star to the antipodal point of that. Then such a function has the property that its degree is an odd number. So here's a problem number 16, which is a variant of that. Show that if you have a function from the circle to the circle, continuous map, which has the property that its value on P star equals the value at P for any P, then its degree is in fact even. So just a slight difference with an antipodal there and no antipodal there. All right, so let's start today by proving the following theorem. There is no continuous function f from S2 to S1 with the property that f of P star equals f of P star for any P in S2. So now we're looking at the two sphere and the one sphere, the circle. And just as we had a notion of antipodal point on the circle, of course, there's also a notion of antipodal point on the two sphere. Right? So we suppose that we have a function with the property that whatever it does to P, the value at P star is the antipodal of what it does to a P. So in other words, for example, if f of P was this point here, then the function would have to have the property that f of P star would have to be here. There's the center. We want to prove that there's no such function. All right, well, proof. Let's suppose that there is. Let's suppose such a function f exists. That one right there. So now what we're going to do is we're going to do what's called a homotopy. So we're going to look at our two sphere, and we're going to think of the equator as being an S1. Okay. And we're going to think of this equatorial disk right there. And we're mapping over to our image circle over here. There's our function f. And we're going to define a family of maps. So we define, say, P sub t from the circle to the circle in the following way. For t between 0 and 1 in the following way. first of all, P of 0 is just our function f restricted to the circle, the equatorial circle. And this line means we take the function f, which is actually a function on all the sphere, and we forget about everything else and just look at what it does to our S1 sitting inside the 2-sphere. So that's just a restriction. Okay, and what is more generally P sub t? Well, it's a combination of doing three things. We're going to first of all shrink the circle just on the equatorial disk. We're going to shrink by a factor of 1 minus t. So there'll be three things going on here. So let's say the first thing that we do is we shrink by scaling by 1 minus t. That stays on the disk. So our circle that we're starting with is being shrunk with the center at the center of the sphere, just shrunk uniformly by a factor of 1 minus t. So when t is 0, we're not shrinking at all, and when t is 1, well, we're going to shrink. So it'll be just the point there. Okay, and that's the first thing that we'll do, and then we'll take a stereographic projection. So we'll take a south pole here, and we'll stereographically project this image onto a meridian circle up here. So stereographically project from our south pole, let's say S. And then we apply F. So this kind of composition means we should first do this. So we take our circle, we shrink it, then we project it up here, and then we apply F. So by the time we get to P1, well, then it's just the final stage. Then at that stage, the circle has shrunk to that point there. The stereographic projection is the North Pole. And then it's just a question of wherever the North Pole gets sent to by F. So P1 is the constant function to the point F of n. N is the North Pole. So we have this continuous family of functions or maps from the same space to the same space. This is sometimes called a homotopy. We'll talk about that later, but there's an example of a homotopy. Continuous transformation from one function from S1 to S1 to eventually a different function from S1 to S1, but continuously deforming all the time. Now we're trying to get at a contradiction because we're supposing that such an F exists. So how can we extract a contradiction from this? Well, first of all, we just look at the beginning and the end points. Okay? The end point is very clear to understand. It's just everything here in the circle is mapping to one particular point. That's a constant map. What about the initial point or the initial function? Well, we're taking this function here, which has this antipodal property, and we're just restricting it to the circle. Equatorial circle, it still has the antipodal property because it has the antipodal property on all of the 2-sphere. So in other words, if we choose 2 points, say Q and Q star, which are antipodal over here, then whatever F is doing, doesn't really matter what it's doing. It's got to have the property that f of q is somewhere over here, that f of q star must be antipodal to it. Because we're assuming that f has this property for any p in the entire 2-sphere. So in particular, it has the property for points on the circle. Okay, so where's the contradiction here? Well, the contradiction is that this final map has degree 0. As a map from the circle to the circle, it's a constant map, so it has degree 0. It winds around 0 times. But this first map that we started with, its degree is, well, we don't know, because we don't know about this f, but we do know from this lemma that the degree must be odd. Because the lemma is telling us exactly that in such a situation, you have a map from the circle to the circle, which respects antipodal points. The degree must be odd. In other words, if we just look at what it does to the circle, it must wind around here an odd number of times. Once, or 3 times, or -1 times, or -5 times. So the degree over here is odd. So we're going from degree odd, continuously, finally to degree 0, which is of course even. And we can't do that continuously. And so that's a contradiction. These two things contradict each other. And so our assumption's incorrect. So the assumption is incorrect. Our next theorem is due to Borsuk and Ulam. And it says that for any continuous map f from the 2-sphere to the plane, there is a point where f of p equals f of p star. So we have our 2-sphere, we have the plane, we have some arbitrary continuous function, no restriction on it this time. Just taking the sphere, deforming it, flattening it so that it's sent continuously to the plane. And the conclusion is somewhere there must be a point P, so that if you look at it and its image or antipodal point P star, then both of these points are sent to the same point in the plane. There's f of p, and there's f of p star. There must be at least one pair of antipodal points that are sent to the same point. Well, the proof is pretty easy with this theorem here. So the proof, well, otherwise, in other words, if there's no such if there's no such point, then we can define a new function, g of p, to be f of p minus f of p star divided by the length of f of p minus f of p star. Okay. So our plane now, we're thinking of it in the usual way, where there's a unit circle, x squared plus y squared equals 1. And so we're supposing that the function there's no 2 points that have this property, so that this combination f of p minus f of p star is never 0. That's what it means, as vectors. They're never 0, so the difference is non-zero, and we can divide by its length. So we require that this thing never be 0, otherwise we'd be dividing by 0. Well, now this is now a unit vector. So what g is a function from S2 to S1. Because after we rescale, we're on the unit circle. And it's continuous. And what happens to it when we look at the antipodal point of P? Where does it go? What is g of P star? Well, if you replace P with P star in here, you're going to get an f of P star here minus f of P here, which is exactly the negative of what's there now. And the bottom is going to be exactly the same. So you're going to get minus g of P. You get the negative vector pointing in the opposite direction. Well, minus g of P is just g of P star. In our coordinate system. So this new function g is a continuous function which has the antipodal property that our previous theorem says is impossible. Previous theorem says that there's no continuous function from the sphere to the circle that has this f of P star equals f of P star property. But here we've cooked up one, this function g. So this contradicts the last theorem. We don't allow contradictions, so our assumption that such a function f exists must be wrong. So this has some curious properties or consequences. Because the two-sphere is like the Earth. So it means, as a consequence, for example, there must be a pair of antipodal points on the Earth's surface with exactly the same temperature and, say, humidity. Well, that's assuming that temperature is continuous, which is reasonable, assuming that humidity is continuous. So what that really amounts to is that here is our Earth, and if here is our temperature and humidity graph, we just imagine having any point P and simply plotting its temperature and its humidity on a graph. Then that gives us a function from the sphere to the plane. And it's just a general function, and this Bourseau-Coulomb theorem is just it applies to general functions. As long as it's continuous, then it must be that there's two opposite or antipodal points that get sent to the same point over there. And getting sent to the same point over here simply means that the temperature and the humidity agree. Okay, what is the ham sandwich theorem? The ham sandwich has to do with, well, okay, it's the picture, I suppose, is a ham sandwich. So you have a piece of bread, bread slice number 1. And then you have a piece of ham. Might be a big, thick piece of ham. And it's a sandwich, so there has to be a top. Another piece of bread. Also has some thickness. So there's bread number 2. And the question is, can we slice our sandwich in half? But we're fussy about the way we want to slice it in half. We want to slice it in half so that both parties get equal amounts of all 3 pieces. So we want to find a cut. We want to slice it in with a plane so that each of the 3 volumes is exactly cut in half. So the theorem says that we can find a plane that slices each of these 3 solids, each of 3 solids, it doesn't have to be these ones, each of 3 solids in half by volume. Okay, so we want to connect this with the previous results. So what we're going to do is, first of all, we're going to orient ourselves with a sphere. So there will be, say, our standard unit sphere in the same space. And for every vector v on the surface of the sphere, we're going to just look at the ham. Okay, so for v on our 2 sphere, well, let's let P of v be the plane normal to v. That splits the ham volume. That splits the ham volume in half. So we're going to forget about the bread, the 2 slices of bread for a second. So there's our ham. And if we're given a direction here, then we're considering planes perpendicular to v. So imagine that plane sweeping through space. Okay? When it's over here, it's got all of the ham on this side. When it's over here, it's got all the ham on this side. And as it moves, it's gradually increasing the amount of ham on this side and decreasing the amount on this side. So if we're just going in this direction, there's got to be sort of some intermediate point where the amount on the one side balances the amount on the other. So we have a plane in this direction, or with normal to our v, which exactly cuts the ham into 2 equal pieces. So there's the cross section, and this are equal volumes. And that plane, we're going to call that P of v.
So that's a plane going through the center.
It's going a plane right through the ham.
No, but on the sphere, it's going through the center of the sphere.
No, this is our reference sphere. Okay, the question is, is this plane going through the center of the sphere? No, our reference sphere is somewhere else. It doesn't have to be near the sandwiches. We're just going to use that to orient our planes. The actual P sub v plane actually goes right through the ham. It just happens to be perpendicular to the direction of v. Okay, now that plane P of v does not necessarily split the two bread pieces in half. But we don't expect it to. So let's record sort of what that particular plane does to the two slices of bread. So let's say there's a slice of bread number 1. So piece of 1, or bread number 1. Okay, that plane is going to slice through the bread number 1. And it still has a preferred direction. And so what we're going to do is we're going to define a number. Let's define b sub 1, which really depends on the vector v, to be the difference between the volume of B1 in the front of our plane P of V minus the volume of B2 behind P of V. So it's a difference of two. Sorry, volume of B1. So B1 of V, it's the volume of B1, the bread, I should say it's the volume of bread 1 in front of P of V and minus the volume of bread 1 behind P of V. So there's our definition of B1 of V. So what we're doing is we're looking at this part. That's the part in front. There's a notion of front because our vector is pointing in a certain direction. Right? So this is in front, and this is behind. And in this case, the front volume is much smaller than the behind volume, so this quantity would be negative in this particular example. Okay, and then we're going to do the same thing for the other slice of bread. So same for bread 2. So we define B2 of our vector V to be the volume of bread 2 in front of our plane P of V minus the volume of bread 2 behind P of V. We're looking for a plane P of V where...
Is there any assumption that you can actually make the cut, so that the cut will actually go through the bread?
No, it might not. I mean, it might be that, so the question is, does this P of V have to slice through the bread? It doesn't have to. If it's at a certain position, it'll just be 0 on one side, all the other stuff on the other side.
Are there any assumptions about the solids being continuous?
Yes, everything is continuous in all this game. Everything is continuous, and as we vary things, all the volumes vary continuously. Sort of our standard underlying assumption in algebraic topology. Things are continuous unless otherwise stated. So we don't want any perverse kinds of volumes here. Okay, so now we're in a position to apply the Borsuk-Ulam theorem. So we're going to define now a combined function, B of V, which is just putting these two quantities, B1 of V and B2 of V, together in a vector. So what is that then? That's a function from the 2 sphere, which is the set of directions, to the plane, because we have 2 coordinates. And so by the Borsuk-Ulam theorem, there must be a point must be a point P on the sphere, so that B of P star equals B of P. But what is B of P star? P star is just the same vector in the negative direction. So that means that the actual plane P of V is going to be equal to P of V star. It's still going to cut ham in half. But now the front and the back are going to be interchanged. So B of P star is going to be equal to minus B of P. Because the direction is reversed. So the fronts and backs are interchanged. And so what we get is that B of, well, let's resort to vectors, B of V star, well, which is the same as B of minus V, equals minus B of V. And that's telling us that B of this particular V has got to be this. Actually, it's both negatives and equal. What do I mean? Well, it means then that for that particular V, for that particular direction, it splits, the plane splits the ham in half because that's how we organized it. But now, each of these two volumes is equal because the image is 0, and each of these two volumes is 0. So it's splitting all three volumes into 2. So in this direction, so our plane P of V splits all three volumes in half. So in the earlier part of the century, there was quite a lot of discussion about the continuum. And some of these theorems were quite useful in deciding some pretty obvious questions, which are rather tricky to answer. So one kind of question is the plane homeomorphic to the line? So homeomorphic. Well, it seems certainly intuitively obvious, but why should the plane and the line be different topologically? Well, the answer in this case is pretty simple. The answer is no. And it's because the line has a particular property that the plane doesn't. If you remove a point, a single point, any point on the line, it becomes disconnected. If you remove a single point on the plane, it is not disconnected. So that's a topological property that's shared by one and not the other. So it's no because point separates A1 but not A2. All right, but then we can ask, well, what about three-dimensional space? Is three-dimensional space homeomorphic to two-dimensional space? Again, our intuition suggests no, but how do we prove that? So there's three-dimensional space, and there's two-dimensional space. How do we, suppose we had a homeomorphism? So again, the answer is no. But we need to argue a little bit more carefully. And the reason is, well, suppose there was a homeomorphism. Okay, suppose that F was a homeomorphism. So look at the image of the two-sphere under this homeomorphism. Forget about everything else, just look at the image of the two-sphere. Well, that's going to be some blob over here. But what do we know about this map? Well, it's a Borsuk-Ulam theorem situation. We have a map from the two-sphere to the plane. What do we know? We know that there's a pair of antipodal points, P and P star, that must map to the same point. So they must map to the same point by Borsuk-Ulam. But that means that that map is not one-to-one when just restricted to the sphere. We were assuming that there was a homeomorphism. Homeomorphism, I remind you, means it's a bijection. It's got an inverse, and everything's continuous. So the Borsuk-Ulam theorem says that if we take the function f and restrict to the two-sphere, it's not one-to-one. Because some pair of antipodal points map to the same thing. So it's not one-to-one, so it can't be homeomorphism.